Plastic is everywhere, from the toothbrush you use today to the phone in your hand, even inside your car, fridge, and medical devices. But have you ever wondered, what exactly is plastic? Why does it melt? Why are some plastics soft and others hard like steel? And why can't all plastics be recycled? Today, we're diving into the science of plastics. Trust me, after this, you'll never look at plastic the same way again. Scientifically, plastics are polymers, long chains made from repeating units called monomers. Think of it like a train. Each coach is a monomer, and the full train is the polymer. These are mainly derived from petroleum or natural gas, forming the backbone of most plastics. However, bioplastics offer an alternative, sourced from renewable resources like corn or sugarcane, providing a more sustainable option for certain applications. Plastics are synthetic, lightweight, flexible, corrosion-resistant, and engineered for thousands of applications, making them incredibly versatile materials in modern society. Let's break down the fascinating process of how plastics are made into three main steps, starting with the initial transformation of raw materials. The first step is cracking. Petroleum is heated to break large, complex hydrocarbons into smaller, more manageable molecules like ethylene and propylene. This crucial process, often involving steam cracking or catalytic cracking, is fundamental to obtaining the basic building blocks for plastic production. Next is polymerization. These smaller molecules, or monomers, then link together to form long polymer chains, which are the essence of plastic. Addition polymerization, for example, is used for polyethylene and polypropylene, where monomers join directly without losing any atoms. Condensation polymerization, on the other hand, involves monomers combining and releasing a small molecule like water, as seen in the creation of nylon and PET. Finally, compounding. The resulting polymer is mixed with various additives such as colorants, fillers, stabilizers, plasticizers, and fire retardants. This crucial blending process ensures the plastic achieves its unique properties, whether it's a specific color, enhanced strength, or increased flexibility. Plastics are broadly classified into two main types, thermoplastics and thermosets, each with distinct characteristics and applications. Thermoplastics, like polyethylene, polypropylene, PVC, PET, ABS, and acrylic, can be repeatedly melted and reshaped without significant degradation. This property makes them generally easier to recycle, as they can be processed and molded into new products multiple times. Thermosetting plastics, such as bakelite, epoxy resin, melamine, and phenolic resin, undergo irreversible chemical changes during curing. Once cured, they form a rigid, cross-linked structure that cannot be remelted, making them strong and heat-resistant. These properties make thermosets perfect for applications requiring high strength and heat resistance, like electrical components and certain industrial parts. The diverse behaviors of plastics, from soft and flexible to hard and rigid, all stem from the secrets hidden within their molecular structure. First, chain length. Longer polymer chains generally result in stronger, more durable plastics, as they have more points of entanglement and interaction. Conversely, shorter chains produce softer plastics, which are easier to process and more flexible for various applications. Second, cross-linking. The presence and extent of cross-links, which are bonds between polymer chains, significantly affect rigidity. More cross-linking leads to greater rigidity and heat resistance, while the absence of cross-links makes plastics flexible, like polyethylene bags. Third, crystallinity. The degree of ordered molecular arrangement influences strength and melting point, with higher crystallinity typically increasing both. For example, high-density polyethylene, or HDP, is much stronger and has a higher melting point than low-density polyethylene, or LDP, due to its higher crystallinity. Finally, additives. Plasticizers can be added to increase flexibility, making a rigid plastic like PVC soft and pliable. Conversely, fillers are incorporated to enhance strength and other properties, tailoring the plastic for specific performance requirements. Recycling plastics is tough due to several complex factors, making it a significant challenge in waste management. Different types melt at different temperatures, making co-processing difficult, and contamination from food or other materials reduces recyclability. Furthermore, thermosets cannot be recycled due to their irreversible chemical structure. and mixed plastics are incredibly hard to separate efficiently. As a result, only about 9% of global plastic waste is successfully recycled, highlighting the urgent need for improved solutions. So next time you pick up a plastic bottle, remember, it's chemistry, engineering, and innovation combined, a testament to human ingenuity. Understanding plastics helps us use them wisely and reduce waste, paving the way for a more sustainable future. If you found this helpful, like, share, and subscribe to SimpleGAN for more engineering content. Comment, which plastic should I explain next?